Okay, this is on polynomial functions. First, anytime you look at a section, you ought to look at the words. Polynomials, remember, when you add or subtract terms together. Okay, and the prefix poly means many, so many terms. And if it's a function, you know, for every x value it's mapped to one and only one y value, and it passes that vertical line test. Okay, first thing the author defines is a polynomial expression in one variable. A polynomial expression in one variable. Okay, and it looks like this. It's a sub 0. Now make sure you write that as a subscript. This is not a sub 0. This is a sub 0. Write it as a subscript. A sub 0 x to the n power plus a sub 1 x to the n minus 1 power plus a sub 2 x to the n minus 2 power. Okay, and then put a plus sign. And to show that they left out terms, they will always use 3 dots. That pattern would continue. And then you need a plus sign on both ends of the 3 dots. And then it's a sub n minus 1 x, and that would actually be x to the first. They don't usually write down the 1, plus a sub n. That is a polynomial expression in one variable. Example would be like if I said 8x to the 4th plus 5x to the 3rd minus 7x to the 2nd plus 6x minus 9, something like that. That is a polynomial expression where you have many terms added or subtracted together. Notice the a sub 0 would be 8, a sub 1 would be 5. It's all the coefficients. All the a's represent the coefficients. Okay? So they will tell you the a sub, and they use I, and that's an apostrophe s. All the a sub i's, that's like the a sub 0, a sub 1, a sub 2, all the a sub i's, and that symbol means is an element of. All the a sub i's are elements of the set of complex numbers. Okay, now you have to go back, and we're going to go back and review. The complex numbers are made up of real numbers and the imaginary numbers. Okay, so that's both. And the n is a non-negative integer. So my n is 4 up here to start. And that makes you go back and review integers. Integers are like the set, and we're going to review it here in a minute, are like the set 0, 1, 2, 3, dot, 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 and negative 1, negative 2. So like 1/2 is not an integer. Okay? So these have to be, all the n's have to be integers. And the a sub 0 cannot equal 0. Okay? Like my a sub 0 would be 8. Okay? So that's a polynomial expression. Okay, now the author's going to take that definition and then give you some problems. Okay? Which of the following are polynomial expressions? Which of the following are polynomial expressions in one variable? Okay, an example. Say they give you 5x squared plus 3x minus 7. Okay, does that fit the definition of a polynomial expression in one variable? are all the a sub i's, are all the coefficients from the set of complex numbers? Yeah, because they're all real. Okay. Is the n a non-negative integer? 2? Yep. And the a sub? Yep. Okay, so this one would be yes. That fits the definition. Okay, another example. 5 divided by x, 5 over x, plus 3x squared. Okay. What throws this one off? Yeah, because that if you rewrote that, you would end up rewriting it. Remember, to bring it up, you make it a negative exponent. If it's positive in the denominator, okay? That's the one that throws that off, okay? Those exponents have to be non-negative, okay? So this one would be no. That's the one that throws it off. Okay, and the third example, negative 3y plus x. Yes or no? Why? 2 variables, yep. Okay, it has to be polynomial expression in one variable, and there are 2 variables. Okay? And you'll find most of the time when you're going through the math sections, you know, for the rest of your math career, every time you look at definitions, and then you use the definitions to help you solve the problems. Okay? Okay, so those are 3 examples. Okay? The next type of problem they will give you is 3 a root. Now, your author may call it a root, or a 0, or a solution. Depends on your author which word they use. These are used interchangeably. Is it a root, a 0, or a solution of x to the third plus 4x squared minus 11x minus 30 equal 0. Okay. There's more than one way to find out if it's a root or a solution. Okay, but one of the easiest ways is to just sub it back in. Does it make it a true statement? Okay, so sub 3 in. Is it a root or a solution? So everywhere you see an x, you just sub in. And what I really want to know is, does this left side equal 30? Okay, take a minute and simplify that. Is it a root? Yes, because you do get 0. Make sure when you're doing this part, everything you did in Algebra 1 and Geometry comes back, like the order of operations. You got to do the exponents first, then you do the multiplying. Remember the PEMDAS? Please excuse my dear Aunt Sally. All of that still holds when you're simplifying. What you've actually found on this is when you say that 3 is a root, that's where that graph would cross the x-axis. Yes, it's one of the places where it crosses the x-axis. It is a root or a solution. Okay? It's the solution. Yeah. Or they're all the same. Some authors call it a root, some call it a solution, some call it a 0. On your graphing calculator, it's called a 0. Okay, it's where it crosses the x-axis. Okay? Okay. The next part, the author talks about the degree of a polynomial. The term degree, in this one we're looking at the degree of a polynomial, is the largest exponent. So like if I have, and they may not write them in order. Usually we try to write them in descending order of the exponents. So you always want to check and make sure they are in descending order. Say I give you 6x to the fifth minus 4x to the fourth plus 9x squared equals 0. Okay, if they ask what is the degree of that polynomial, the degree is 5. It's the highest exponent. So the degree is 5. It's that highest exponent. Okay? Okay, if they said what's the degree of a polynomial, anybody remember that one? What if I gave you a term like this? If I gave you what's the degree of that monomial? That's where you add them. Okay? The degree of a monomial is where you add them. You'd add, and the degree of that would be 16. Polynomial, you take the highest degree. Those are good ACT compass type questions. Okay? See if you know your degrees. Okay? The other thing they talk about, let's go back to this problem here. The other thing they talk about is the leading coefficient. The leading coefficient is you look at the term with the highest exponent. Okay? You want to make sure it's in descending order. So you got to find the term with the highest exponent. Okay, and it's this number in front. So on this one, the leading coefficient is 6. Okay? Okay? Okay. I want to go back through, and this is going to take probably a half page or more. Okay, so if you need to turn your page, okay, and start down towards the bottom of your page. Okay, when okay. Okay. When we look at all the different sets of numbers, okay, all the different types of numbers, okay, and I always tell kids, you know, when they have a baby, you ought to start counting with that baby from day one, otherwise you're behind. Okay, forget about the ABCs. Oh no, don't do that. Okay, but you ought to start working with the numbers. When you start counting with a baby, you don't start with 0. You always start with 1. So when they get to that first birthday, you can say, how old are you? I'm 1. Okay? So natural numbers or counting numbers. That's the first thing we start with. Our natural, and we're going to go up on this. Natural numbers or counting. I'm down at the bottom, just so I have enough room. We're just going back and reviewing what each one of these, natural numbers or counting numbers. Natural numbers or counting numbers start with 1, 2, 3, ... and they are a set. When they're a set, use the braces. Okay? Natural numbers or counting numbers start with 1. Okay? Then at a certain point in our lives, we learn about 0 because usually somebody takes something away, okay, so that you're down to nothing, you're down to 0. Okay? When you put those two together, the natural numbers and the counting numbers, you'll end up with 0, 1, 2, 3. Okay, and go up. That is the set of whole numbers. Whole numbers are the set 0, 1, 2, 3, and so on. The 3 dots shows that it continues on. 0 is a whole number. 0 is not a natural number. Okay? If you take the whole numbers, come over here and put in the negative integers, please spell this correctly. It's I-N-T-E-G-E-R-S. A lot of people say inter, like they put an extra R in after this E. No, negative integers. Okay, and the negative integers will actually go this way. They go -1, -2, -3, ... in that direction. If you put the whole numbers and the negative integers together, then you end up with the integers. You will see this set a bunch in math. The integers. Okay? The set of integers are 0, 1, 2, 3, ... in that direction, and -1, -2, -3, ... in that direction. 1/2 is not an integer. Okay? It has to be in that set. Okay, if you take the integers and then put in the fractions with the integers, if you put the fractions with the integers, you end up with a set called the rationals. Okay, the rational numbers, or the rationals. Rationals are in this form, A over B. Like 2/3 is a rational number. 5/8 is a rational number. 6 is rational because I can write it 6 over 1. Okay? Okay? And there's some restrictions on this. A over B, where A and B, this symbol means is an element of. A and B are elements of the set of integers. Okay? So, for it to be a rational number, the numerator and the denominator have to come from this set. Okay? You can't have like a square root of 5. Okay? The other thing on rationals, if you look at decimals, if I did decimals, for decimals, they are terminating decimals like 0.5. That is a rational number because I can write it like 1/2. Or repeating decimals like 0.333, repeating, I can write that like 1/3. So those are rational. They can either be in the form of a fraction, A over B, where A and B are integers, or a terminating or a repeating decimal. The B can't, yeah, better put that on there. B cannot be 0, because you'd have division by 0. Thanks. Okay. You can also put the decimal examples like 0.5, it stops, or 0.33 repeating. We usually show a bar above it to show it's repeating. Okay. Okay, then if you take the rationals, whoops, sorry, and if we add another set to it, the irrationals, and you worked with these in Algebra 1 and Algebra 2 when you did the square roots. The irrationals, I'm not going to write down the whole definition, but basically they cannot be put in this form. Okay? Examples, like the irrationals, I'm just going to give you some examples, like square root of 2. No matter how hard you try, you cannot put that in the form a over b, where a and b are integers. Square root of 3 is another example. Square root of 5 is another example. Probably the most famous irrational is pi. Okay? And as far as decimals, they are non-terminating. That means they don't have an end. They are non-terminating and non-repeating. The bad part on pi is a lot of times we round it to 22/7 or we round it to 3.14. But they've put that in on super Cray computers. There is no repetition, there's no termination. Okay? Okay, now, if we put the irrationals and the rationals together, we end up with what they call the real numbers. The reals. Okay, and the reals are all the numbers on the number line. All the numbers on the number line. And that's, the reals are what you worked with in geometry, Algebra 1. But then in Algebra 2, we took it up a step. In Algebra 2, we took it up to, if we put in here the pure imaginaries, that would be like 5i, okay, 3i, negative 2i, or it's just an I value. Those are the pure imaginaries. If you put the pure imaginaries and the reals together, in Algebra 2, you finally got to the complex numbers. Okay? And the complex numbers are in the form of a plus bi. This is the real part, the a, and the bi is the imaginary part. Okay? So we're working in the complex number system, okay? But if they give you directions and they say, you know, your answers have to come from the set of integers, okay, now you know what it should come from. If you have a number, like say pick a number out like 5, okay, you should be able to go figure out where it starts. 5 would be in the natural or counting numbers. If it's in this, it is a whole number. It is an integer, it is rational, it is real, it is complex. Because I can write 5 as 5 plus 0i. So pick any number and figure out where it starts. Okay? Say I pick like 3/4. 3/4 is not natural, it's not a whole, it's not an integer. It finally fits. 3/4 is rational. If it's rational, it's also real. If it's real, it's also complex. You can just work your way up the chart. Make sense? Okay? Okay. Now, with that in mind, the author is going to give you another example to work. In the directions, it says write a polynomial equation of least degree for the roots 3i, 5, and negative 4. Okay, what the author's saying is these are the answers He wants to know what's the beginning equation. The first thing you have to look at is this. The author's not telling you all the roots. Conjugate imaginaries always occur in conjugate pairs. You remember solving quadratic equations last year and the answer was like 5 plus or minus 3i? Negative 2 plus or minus 8i? They always occur in pairs. So, the author's not telling you everything. If 3i is a root, what's the other root? Negative 3i. The author does not have to tell you that. You have to know that. Okay, and I always work my way back. Okay? If 3i is a root, let x equal 3i. If 5 is a root, then x equals 5. If negative 4 is a root, then x equals negative 4. And x equals negative 3i. Okay? Now get them equal to 0. Subtract 3i. If I take this 3i over to the other side, I'm going to subtract it. So I'd end up with x minus 3i, and I'm getting the factors. Subtract the 5. So I'd get x minus 5 equals 0. This one I have to add 4. So x plus 4 equals 0. And add 3i. So x plus 3i equals 0. Put the I factors together. Okay, group them together. So I'm going to group the x minus 3i and the x plus. Notice I don't have the equal sign. We need to multiply these factors out and group the x minus 5 and the x plus 4. We're working our way back to find the beginning equation. Okay, group these two together and then group these two together. Okay, now some of you will be able to do this by sight. This is using what you learn on factoring. If I multiply out a minus b times a plus b, what's the shortcut? Anybody know? Okay, let's say I don't know. ba squared plus ab minus ab minus b squared. What happens to the middle term? Drops out, right? Now you get the difference of two squares. Do you remember that? Difference of two squares? Okay, so I can do this the long way, but I'll show you the shortcut too. Let's do it the long way. If I multiply this out, and I recommend you draw the arrows if you don't know. So it'd be x squared. Multiply this out. It'd be plus 3ix. Put the coefficient in front. Okay, and then go underneath. This would be minus 3ix. And this would be minus 9i squared. Okay, let's go ahead and simplify just that much. So this would be x squared, middle term. Drops out. What is I squared? Negative 1. Okay, so this is like minus 9 times a negative 1. So this is like x squared plus 9. That part simplifies all the way down to that. Okay, now let's simplify this. Now, if you can do the shortcut, like if you know you're factoring and multiplying good enough, you can do the shortcut. If not, multiply it out. So this would be x squared plus 4x minus 5x minus 20. And you still need the equal 0. Combine like terms. You get x squared, then what? Minus x. Minus 1x or minus x minus 20 equals 0. So we're down to multiply these two out. Okay. So now you got to multiply. There is no shortcut on this part. You got to take x squared times everything. Remember, when you're multiplying, you add the exponents. Check my arithmetic. Okay, and then you got to multiply 9 times everything, and then you got to combine like terms. And it still equals 0. If you leave the equal 0 off on the test, I'm going to take off points. Okay, combine like terms. We've got an x to the 4th, a negative x squared. Okay, now these two are like terms. Oh, sorry. My fault. Thanks. Okay, so the next two are like terms. What am I going to have? Negative 11x squared minus 9x minus 180 equals 0. So the directions were to find the polynomial equation that has those as answers. If we worked it backwards, we would factor it back into those and get those 4 answers. This tells you how many answers there are. There are 4. Okay? It just happens that 2 of them are imaginary and 2 are real. Okay? If you can do this up here, if you can do this by sight and get down to this, it'll save a step. Okay? Should be able to do the x squared. Okay, plus 4x minus 5x would be minus x and then minus 20. If you can skip that next step and go to the 3rd step down, that'd be great. Okay? Okay, that should get you started on that first section. If you've got time, today this is the first day on, we have about 6 minutes left. If you have time, hand in the notebooks today. We only have 6 minutes, so if no time today, AP will not work because we're doing class meetings, etc. So hand them in tomorrow. Okay.